Welcome back to the Mechanics of Solids lecture series. We're working examples of shear and bending moment diagrams. The next example we'll look at is a simply supported beam with overhang, a 10 kip load between points A and B, a 5 kip per foot distributed load over this region here, and a 4 kip per foot distributed load on the end. To save some time, I've already calculated the reactions in the y direction at support A equal to 2 kips pointing upward, and support B equal to 38 kips going upward. I've also extended the lines down at each region of load discontinuity so we can identify the changes in the shear and moment diagrams. And I've drawn an axis for the shear diagram, labeled it with the units in kips, and an axis for the moment diagram, labeling with the units of kip feet. We'll start with a shear diagram working from left to right. At point A, you have a 2 kip reaction pointing upward. That tells me the shear diagram is going to jump up by 2 kips, and then in the region from A to the next point load, shear will be constant. So we draw a straight line going across and label it with the value 2. And then at the 10 kip force pointing downward, the shear diagram jumps down by 10. We'll keep track of our calculations over here in the margin. 2 minus 10 equals -8, so it jumps down to -8. Then in the next region, shear is going to be constant where there's no load until we reach the distributed load of 5 kips per foot. As the distributed load is acting downward and it's uniform, the shear is going to decrease linearly, so we know it looks something like that. I can calculate the value at point B as the value at the beginning of the distributed load minus the value of the load, 5 times the length over which it acts, which is 2, and that gives me -18. Now at support B, I have a 38 kip reaction going upward, so this is going to jump up by 38, and I calculate the value on top as -18 plus 38 equals 20. And let me label both this value 18 and this value up here as 20. Finally, in the region from B to C, we have the 4 kip distributed load acting downward, so the shear is going to decrease linearly, and we expect it to go back to 0. So I'll draw that as a straight line. 20 minus the value would be 4 times the length over which it acts, 5, equals 0. So that does confirm that the shear goes back to 0 at the end. Now for the moment diagram. We're starting at point A, working from left to right. Point A is a pin support, so the moment has to be equal to 0. Then over the next part of the diagram, the shear is constant, so the moment is going to increase linearly. We calculate its value as the area under the shear diagram, which would be 2 times the length over which it acts, 4 equals 8. So this value is 8 right here. Then over the next region, the moment diagram is going to decrease linearly because the shear is negative and constant. So we can calculate the value as the value at this point minus the area of the shear diagram over that region, minus 8 times 4, which gives us a -24. So shear drops down like that. And then over the next region, because the shear is negative, the moment is going to decrease, but the shear has a slope to it, so the moment is going to have some curvature to it. It's going to be a quadratic curve. And it's going to look something like that. Okay? How do I know that? I know that the slope or the curvature increases as the value of the shear increases. So I expect the curvature to be sharper at this end than at this end, and that's how I know how to illustrate it. So the value at this point we can calculate as -24 minus the area of that little trapezoid, which would be 1/2 times the sum of the values at the endpoint, that's the average height of the trapezoid, times the length of 2, and that gives us -50. So this value right here is 50. And then finally, over the last part, the shear is positive, so the moment's going to increase. The slope of the shear is linear, so again, the moment diagram is going to be quadratic or have some curvature. I'm going to draw it like that. And how do I know? Again, I know that the curvature is going to be larger where the shear is larger. And in this case, the curvature should actually come back to 0, or the slope of the moment diagram should be 0 where the shear is 0. So that helps me get the shape of the curve. I do need to check that it comes back to 0 as expected. So we have -50, which is the value at point B, plus the area under the shear diagram, the area of that triangle, 1/2 times 20 times 4, and that indeed equals 0. So that's a good check. And let me just note that all those portions of the diagram are negative, and this example is complete.